Dear everyone, this is Jian Weng, a fourth-year PhD student from UCLA. Welcome to our work unit, Unifying Tensorized Instruction Compilation. This is a collaborative work between UCLA and AWS. This is motivated by the increasing demand of computation in DNN models. Researchers have developed many software and hardware mechanisms to reduce the compute and memory burden in these workloads, and mixed precision is one of the most widely adopted techniques. Inputs and weights are cast to lower precision to save compute and memory burden, and outputs are in higher precision to retain the accuracy. However, as it's shown in the figure, blindly casting the data type without specialized hardware support can hardly gain performance from mixed precision because of the overhead of casting the data type back and forth. Therefore, hardware vendors provide specialized instructions for this emerging computing idiom in mixed precision models. Multiple inputs with lower precision are reduced to produce outputs with higher precision. For example, Intel Vini performs 16 8-bit dot products, and each dot product produces 32-bit results. And NVIDIA Tensor Core performs a 16 by 16 by 16 FP16 matrix multiplication, and the results are in FP32. In the rest of my talk, instructions specialized for this idiom are called tensorized instruction. Reorganizing the loops and rewrite them with a tensorized instruction is called tensorization. Unlike conventional SIMD, the tensorized instructions are no longer element-wise, and the data type of input-output operands are no longer identical. So the high-level abstraction and compilation techniques are still very preliminary. In practice, if we want to use these instructions, we can either use vendor-provided libraries, which is limited to predefine the kernels and lacks further optimization, or write hardware intrinsics manually, which is difficult for programmers. Prior works tried to achieve both flexibility and accessibility by developing DSL compiler for each single instruction. This requires excessive efforts when there are too many instructions. In this work, we present an extensible, productive, and high-performance compilation flow for tensorized instructions based on a tensor domain-specific language. The big idea of maintaining a unified compilation flow across diverse tensorized instructions is to have a unified instruction description so that we can reuse the analysis and the code transformation process. After rewriting the program with the tensorized instruction, we also provide tuning strategies to automatically get favorable performance. As aforementioned, UNIT is based on a tensor domain-specific language. A tensor domain-specific language typically refers to those languages follow this paradigm. Users declare tensors by their shapes and data type, and loops by their types and trip counts. By type, we mean either its data parallel or reduction. The computation is described by expressions involving these tensors and variables declared. In the figure above, we show how a convolution is implemented in this domain-specific language. Besides the declaration and the expression, the DSL also provides a set of interfaces to reorganize the loops, like splitting, reordering, and unrolling. These are very useful for the instruction rewriting and the performance tuning, which will be used later. Next, let's go through the compilation flow step by step, and the first part to cover is the instruction description. Besides the tensor program itself, the instructions are also described in the tensor DSL, which makes the instructions tractable by the compiler infrastructure. As it's shown on the right-hand side, the declared tensors represent the register operands, and the expressions describe the arithmetic behaviors of the instructions. All the information gathered from the tensor DSL include the shape of the tensors, the type of the loop variables, and the computational expression. Next, I will demonstrate how the analysis and transformation use this information to determine if and how a tensorized instruction is applied on a given program through an example, whose tensorized instruction is interVinny and the tensor program is a convolution. To determine the applicability of a Vinny on a convolution, a very first question to answer is if the computation of the convolution can be represented in Vinny. We inspect both expression trees of the convolution and Vinny to match the arithmetic operation and the data type on each node. In this case, these two trees have exactly the same topology and the attributes on each node are exactly the same. Therefore, we pass the first phase of inspection. Next, we need to determine the loops to be tensorized, which is essentially a mapping from a subset of the loops in the program to the maps in the instruction. Note, mapping can only happen between loops with the same types, say data parallel to data parallel and reduction to reduction. This is why I still keep the highlight of the colors here. We enumerate this mapping, and here we map K to I and RC to J. Then we check if this mapping is feasible. Checking the feasibility of a mapping is equivalent to doing something like this on the imperative loop nest IR. The selected loops are splitted by the corresponding loop trip counts in the instruction and reordered to the innermost. Then we require the memory accessed in the shadowed region is a subset of the memory accessed in the instruction. We formally defined the subset in our paper, but here it's enough to know that B and C access exactly the same amount of memory as the instruction, and A access less than the instruction. Therefore, this mapping is feasible. And we're gonna finalize the loop splitting and reordering. The terminology of broadcasting and concatenation will be explained in the following slides. For now, we know how the loops should be reorganized to get ready for code rewriting. And the last missing piece of code generation is how can we plug in each operand of the instruction. As aforementioned, we are gonna tensorize K and RC, and the innermost shadowed region will be rewritten by Vinny. We need to figure out how each operand should be prepared and fed to the instruction. Because of the diversity of the potential hardware we will target, it's almost impossible to find a fully unified methodology to generate the operands. For example, Intel AVX provides vector load store intrinsics to prepare the operands, but NVIDIA Tensor Core only offers opaque buffer load intrinsics. Therefore, here we expose a callback interface to the compiler developers, so that they can implement this function to generate the operands based on the information provided, including the array pointer and the data access pattern. Let's take the array access of A as an example. From inner to outer, the trip count of tired RC is 4 and the coefficient is 1. So this loop level is vectorized by 4. And then we go to loop level K. For the coefficient, it's 0, which means the index does not change when K changes. So the value should be broadcasted along with K. This IR expression returned by this callback function will be embedded in the imperative IR and lowered to AVX 512 vector load intrinsics when code generation. And similarly, other operands can be generated in this way too. Finally, in the code generation phase, the compiler driver invokes each callback function to prepare each operand and plug them in the tensorized instruction. So much for instruction rewriting. The outer loops are still open to reorganization for performance tuning. All the CNN layers follow the same idiom shown in the code snippet on the right-hand side. Perfect loop nests composed by multiple levels of data parallel and reduction loops. For both the CPU and the GPU, our generic tuning strategy exploits both the chorus grain and the fine-grained parallelism. By chorus grain, we mean the parallelism achieved by multi-threading and multi-core. By fine-grained, we mean instruction-level parallelism achieved by thread-based pipeline execution. More specifically, when putting a reduction loop in the innermost, the loop carried accumulation may cause read-after-write hazard penalty, which should be avoided. For CPU, achieving coarse-grained parallelism is to distribute data parallel loops on multi-threading, and achieving fine-grained parallelism is to reorder and unroll a small degree of data parallel loop under the innermost reduction loop. The key to this tuning strategy is to have a proper pair of degrees of multi-threading and unrolling. Here we enumerate two breaking points on the data parallel loop nest. Loops will be splitted by these 2 points. Loop nest above the first point will be executed by multi-threading. Loops between these 2 points will be executed serializingly. Loops under the second point will be reordered and unrolled under the innermost reduction loop to avoid a pipeline penalty. We try each of them and use the one with the best performance. Analogously, on GPU, to achieve coarse-grained parallelism, we first launch the kernels on multiple GPU blocks. However, if we just directly accumulate the result of matrix multiplication, it lacks data reusability and suffers from pipeline penalty because of the innermost reduction loop. Instead of accumulating a single element, we accumulate a P by P outer product by splitting 2 data parallel loops by P and reorder them to the innermost. By outer product, we mean a matrix multiplication between 2 vectors. One is P by 1 and the other is 1 by P, so the product is P by P. By doing this, each loaded memory buffer of A and B are reused P times, and the pipeline penalty is hidden by the splitted data parallel loops. Now, there is a trade-off between the fine-grained and the coarse-grained parallelism on GPU, since both unrolling and kernel distribution are applied on data parallel loops. The more memory reuse we want, the less cores we can utilize, and the more register pressure we have. Therefore, in this work, on the GPU we used to run the experiments, we only make P equals 2. So much for the generic tuning strategies. On GPU, we also developed 2 strategies specialized for CNN layers. CNN layers often have very small width and height and very deep input channels. They both can benefit from specialized tuning strategies. We first specialize for small width and height. If it cannot be perfectly tiled, we need to pad it. For example, for a 7 by 7 tensor, to make the width dimension tileable by 32, it wastes more than 3/4 of the memory bandwidth. The optimization we apply here is to pad 2 dimensions respectively and fuse them into one. By doing this, only less than 1/4 of the memory traffic is wasted. However, greedily applying this strategy does not always help the performance, because sometimes the overhead of data rearrangement is larger than the benefit of saving the memory traffic. Therefore, we will try both padding the fused dimension or a single dimension when tuning the performance. We then specialize for the deep input channel. On CPU, it's hard to parallelize these loops because of the high overhead of synchronizing the threads for only a small number of elements. On GPU, we can accumulate the result on local registers and store the partial sum in the shared memory. Before reducing the partial sum in the shared memory, we can use a blockwise barrier to synchronize. Choosing a proper degree of splitting the reduction loop is important. We do not want the number of threads is either too small to hide the memory latency or too large, which imposes a high register pressure for the context switching and the synchronization. Therefore, when tuning the performance, we try each divisible degree of multi-threading, and the default is to use as many threads as possible. So we are done with the technical details, and here we come to the evaluation. All of our experiments are conducted on Amazon EC2 instances listed above. We use ALVM10 as our code generation backend for all the platforms. We use CUDA 10 as our GPU assembler and runtime. We compare against the vendor-provided high-performance kernel libraries with tensorized instruction integrated as our baseline. All the models are batch size 1 and from MXNet Model Zoo. They are converted to TVM Graph IR and Relay IR and for tiling-friendly data padding and locality-friendly data layout alternation. We evaluate our compilation flow along with two lines, performance and extensibility. For the performance, we first compare the end-to-end performance on 9 popular DNN models. Then we incrementally enable each tuning strategy to see their impact on performance on each single layer and explain why we can or cannot do better. We also stress our compilation flow on ARM VDOT to demonstrate the extensibility. On server CPU, we can outperform inference models with 1DNN integrated by min 1.3. And the two models we do the worst are ResNet 50 and ResNet 50B, since Intel engineers tune these two models really hard, and we can still outperform them. And on NVIDIA Tesla V100, we can outperform cuDNN by min 1.75 because of our generic and specialized tuning strategies. Next, let's go to the Appellation Test to study the impact of our tuning strategy on the performance. Here we select the 16 representative layers for our ablation study, and each bar of performance is normalized to 1DNN performance. Here parallel means we only apply cross-gram parallelism, plus unrolling means we additionally apply fine-grained parallelism by using a heuristic function to estimate the quality of each pair of breaking points, and greedily use the one with the best estimation. Plus tuning means we first try 8 pairs of the breaking points in the descending order of the heuristic. If we find a better solution in this 8, we try another 8. We find that this heuristic is already very effective. 95% of the optimal points fall in the first 8 points, and the performance is slightly improved by tuning. As you can see, the performance of 1 and 4 are poor because their width and height shapes are relatively large prime numbers, which can neither be fully unrolled nor perfectly tiled. In TVM, this case is handled by a if guard, so the branches kill the performance. For GPU, we still use those 16 layers, and the performance are normalized to cuDNN. Plus FuseDIM and plus split K means we greedily apply each optimization with the default parameters. Plus tune means we explore the tuning space and choose the one with the best performance. Similar to CPU, tuning slightly helps the performance too. As you can see, point 1 and point 15 are poorly performed because their strides are not 1, which breaks the data contiguity. Because of the opaqueness of tensor core buffer loading intrinsic, we need to rearrange the data in a compact layout when runtime, which kills the performance. To demonstrate the extensibility of our compilation flow, we also stress our compilation flow on a new hardware platform, ARM. Instead of building a new compiler for ARM.dot instruction, we only need to describe the ARM.dot instruction and plug it into the compilation flow. All the efforts we did for x86 CPU can be easily utilized on this new instruction to get high performance. Finally, to conclude our work, UNIT provides a unified compilation flow for the emerging tensorized idiom as well as the high-performance tuning strategies. I'm currently actively coordinating with the TVM community to get it integrated to their new scheduling system. For the future work, for now, we highly rely on the data layout alternation to get high performance. We want to have a feedback path to relay so that we can make our tensorization mapping enumeration to guide the data layout alternation. Another ambition is to integrate this idea to general-purpose compiler as an extension to the vectorizer. This work will be presented on Session 2 of CGO main program on March 1st, 11:40 a.m. I'm looking forward to seeing you there.